Thank you for coming back again. We are going to look at electromagnetism, but the subtopic is on Lenz's law. Lenz's law is our focus this morning. If we understand it step by step, look at Lenz's law step by step, you should be able to understand how to solve problems in it. And once again, as you study physics, always remember that you need to do a lot of output revision in order to improve. Alright, do not just do input revision by reading and reading your reference book. It is not good enough. You need to answer a lot of questions and you need to look at past year questions, write down your answers and work at it. Then you will improve very fast. After today's lesson, you should be able to master the concept in Lenz's law and you should be able to solve problems that involves Lenz's law. Alright, or Lenz's law rather. Let us take a look at the question straight away. Which diagram shows the correct direction of the induced current when the magnet is moved in the direction shown? So there are 4 situations here. Every situation is different and we will need to know which one is the correct one. Because as the magnets are moved in, you know that according to electromagnetic induction, there is an induced current that is formed in the circuit. And the galvanometer here, it will show a deflection. So now, the emphasis is this. Which one shows the correct direction of the induced current? The emphasis is in direction. Alright, everybody says direction. Okay, good. Just remember, direction of the induced current, it is the focus of our discussion. Now, whether you like it or not, we need to read this statement again, and then I'm going to explain it as I go through with you how to get the answer. Lenz's law states that the direction of the induced current is such that its magnetic effect always opposes the change that causes the magnetic effect. I know I have every student telling me and said, Uncle Pang, how to understand a statement like this? Alright, so I'm going to explain this statement to you by looking at this question and explaining to you how to get the answers. This is our question. Which of the diagram, or which diagram shows the correct direction of the induced current when the magnet is moved in the direction shown? Now I'm going to do it one by one. Alright? Every step, one by one, and then I'm going to explain it. So, look at answer A. The magnet moves in. Alright, I'm going to label it. I call this X. Alright, I call this X and I call this Y. Because if I have X and Y, I can refer to it. It's very easy. And if you look at the coil here, alright, there is a coil of the wire, alright. So I'm going to refer to the coil XY and end X and end Y. So you will know what I'm talking about. Okay, first question. As the magnet moves in, it will produce an induced current. Alright, so what do we observe in G? There will be a deflection. Alright, deflection in the galvanometer G. Alright, so far so good? Now this deflection in G tells us that there is an induced current. Okay? We did not have any power supply here. That's why it is called an induced current. Alright? So, come again, we have a deflection. What does it tell us? There is an induced current in the galvanometer, in this circuit. Now, because there is a current, there is an induced current. So the coil XY, what has it become? See, very good. You are discussing among yourselves and you know what it has become. You have learned that for a coil that has a current, it becomes an electromagnet. Very good. So I write down now, XY becomes electromagnet. So the coil XY has become an electromagnet. And if it has become an electromagnet, it definitely has a pole, north pole, south pole, right? So now we have to ask the question, is X north or south pole? So that will be a very good question to ask. I'm now considering, remember, I'm considering answer A, alright, just as one of the situations. So X and Y, one of it must be north, the other must be south. We have to determine which one. That's where Lenz's law comes in. Alright? That's where Lenz's law comes in. Now, X. According to Lenz's law, X must be the north. Alright? X must be the north. Okay, I just summarize it. X is the north pole. Why do I say that? Because as you look at the magnet, now as the magnet is going in, alright, I think you can see my pointer now. Now as the magnet moves in, okay, as the magnet is pushed in, alright, according to Lenz's law, the direction of the current must be flowing in such a way that its magnetic effect, meaning that it has become an electromagnet now, XY, it opposes the magnet moving in. Because the magnet that goes in, it produces the induced current. So now X has become the north pole. X is saying, hey, alright, because it opposes. In other words, it is as if it does not want the magnet to go in. It opposes. There is an opposing force. And for that to happen, X must be the north pole. Because north and north, there is an opposing force. It repels each other. Alright? Now we have to determine, okay, so far I understand you are telling me. So now we have to ask, is A the answer? Now I'm going to write down X, this is the north pole. Alright, so now we take our right hand. Okay, I'm going to take my right hand and put it at X. Okay, I'm going to use it on the screen so that you can see it. Alright, now my thumb, my right hand, I must use my right hand. The thumb points to the north. And then it grips this way. Alright? So my fingers grip this way. It goes in. So the current actually goes in. Alright? Do you see the point? It goes in. Alright? So I'm going to write it down. So it should go in. What I am indicating in red is the correct one. So in other words, is the answer correct? Okay, please show me by using your head body language. If it is wrong, shake your head. And if it is right, you nod your head. Alright, so is A the answer? Alright, very good. I see one of you, you have got the answer and you know that it cannot be the answer because the direction here is not the direction that I have indicated, isn't it? So far, so good? Alright, very good. I think you look satisfied and interested. Let us take a look at answer B now. Alright? So far, so good? Now, I'm going to erase this. I just assume that you have copied down everything that I have written so far. Alright? So, A is not the answer. Okay, because it is opposite to what is given. Okay, now let me erase this, and I'm going to take you through B. Now it is good for you to write things down over and over again. Alright? Let's take a look at B now. Now I'm going to use different symbols just to help you. Alright? This will make things easier. Alright, I call this LM. Alright, I call this LM. This in answer B. I'm going to take you through answer B now. Okay. So now this magnet is going in. Alright, this magnet is going in. So as it goes in, what do we observe in the galvanometer? What do I say in the galvanometer? Deflection. Alright, so deflection, we will observe that there is a deflection in the galvanometer G. And what does this tell us? There is an induced current formed. Very good. Induced current. Okay. And since there is an induced current, what has Lm become? The coil Lm has become or I just write down becomes electromagnet. And since it has become an electromagnet, L and M must each have a pole. Alright? The poles of a magnet, north or south. Okay? So now we have to determine. Alright, I'll just take L. Just take L. Alright? I will highlight for you. Okay? Take L. L must be the north or south. Now look at the magnet here. The magnet here, the south is going in. Alright? So in order to oppose the magnet from going in, according to Lenz's law, L must be the south. Okay? So L is the south pole. Alright? So I will write down L becomes south. Alright? L is the south pole. I just put south. Okay? So I will write then down. I will have to write it down. So L is the south pole. Okay? So if L is the south pole, M must be the north pole. Now I'll go to the screen again and use the right hand grip to show you what happens to the direction of the current. Alright? North, the thumb, right hand, the thumb always points to the north. Okay? So the other four fingers come down in the grip. So the grip is the direction of the induced current. Okay? So induced current, it comes out. So I have to mark it. So I have to mark it. It comes out. Okay? It has to come out. It has to come out. Okay, once again, I'll test you, right? Okay, you respond to me, please. Boys and girls. Is B the answer? Is B the answer? Show me. Alright, no. Very good. So B is not the answer. Because you see, it should be coming out, but it is going the other way. So B is also not the answer. Now I'm going to erase part of it because the rest of the sequence, they are very similar. I'm going to look at D. Because of time factor, I will jump straight to the final answer D. We'll go through with it and see how it is. Alright? So I take this off. Okay, I'll just fill in the blanks because the rest of it is the same or similar rather. Okay, now I'm looking at answer D. Okay, I'm looking at the situation in answer D. Alright? In answer D, when the magnet moves out of the coil, you will also see a deflection in the galvanometer. In other words, we say that there is an induced current in the circuit. Very good. Continue. So in other words, the coil, I can call it another, I label it another name, I call it PQ. Alright? I call it PQ. Okay. I like the alphabet P. P for punk. Okay, so, alright, I have the coil PQ. I write down what has become of coil PQ. So because there is an induced current as shown in the deflection, we know that PQ actually has become an electromagnet. So coil PQ becomes electromagnet. Alright. Now, if that is the case, P must have a pole. Okay, so I want to write down P is the, fill in the blanks. Is it north or south pole? Okay, now you look at the magnet. Now the magnet is going away. Alright? The magnet is going away. According to Lenz's law, it opposes the magnet going away. In other words, it does not want the magnet to go away. Do you get it? So the magnet here, alright? Okay. So the magnet here wants to go away, but this coil PQ does not want the magnet to go away. It wants to attract it back. So P must be which pole? P must be the north, so that it will attract the south. Okay, it doesn't want it to go away. Alright, so P is the north. Okay. Now remember, I always tell my students, Lenz's law reminds me of a love story. You know why? Because you look at case D. Case D, the magnet wants to go away. But P is the north pole. It doesn't want the magnet to go away. It has to be the north pole. So it is as if the coil PQ is telling the magnet, darling, please don't go away. Come back. Come back. Please don't leave me. You know, it is that kind of drama, love story. There is love story in physics, you know. Alright? So, P is the north pole. It is attracting the magnet back. Alright? So far, so good? Alright. Now, again, I'm going to go to the screen and show you. Alright? P is the north. I'm going to write it down. P is the north. Alright, the north pole. Q is the south. So here, I'm going to take my right hand and I'm going to grip it. My thumb points to the north. Okay, so it goes in, isn't it? So this field will be going in. Alright, it goes in, so the current goes in. I'm going to mark it. Okay, so it goes in. Get it? Alright, now you tell me, is D the correct answer? Come on, show me by nodding your head or shaking your head. Okay, very good. So, some of you have responded. You have found that, okay, correct. So now D is the answer because the current shown is correct. The other cases, they are wrong. Okay? So, with this explanation, I hope you have understood Lenz's law much better. So in a sense, this objective question is very good because this test question allows me to explain to you one case to another case. There are altogether 4 cases. Alright? So with this, I hope that you would have learned Lenz's law again and you are able to answer questions on Lenz's law. Alright, with that I would like to say thank you very much and may God bless you. I'll see you again. Uncle Pang here.